we were discussing advanced representation, and now I would like to go through a little bit complex example. The example comes from the information retrieval domain, and basically is about using derived data. You take the initial data of the domain, you add some derived data. And I really like this example because it is a perfect example of how to design a visual analytics application. In my opinion, one of the most exciting part of the story is that being a visual analytics and visualization in general, orthogonal to different domains, if you go in this direction, you will meet totally different requirements, totally different users, cybersecurity, medical application, or information retrieval. And that for me is nice because I am a curious person, so I got a lot of information about different domains. And here I'm trying to come up with some, let's say, general overview of the steps that you go in designing a visual application, visual analytics application. So let's go in this example. First of all, the context. And this is the step one of designing a visual analytics application. You have to understand the domain of just a moment. You have to understand the domain of the user, what you're talking about. Here we are talking about information retrieval. I suppose that some of you are familiar with it, but I can bet that some of you are not. And the main point about information retrieval is that it is an experimental field of research. You're not theorem here. It's not like the relational model in which you have a normal form or whatever. You go for experiment. To evaluate how good is an information retrieval engine, you have to go to experiment it in practical. So in the last 20 years, let's say 30 now, a lot of large-scale evaluation campaigns have been designed and applied. So our evaluation campaign, meaning that the main goal is to evaluate the result of the information retrieval engine, the performance. And among them, one of the most relevant in USA is TREC, Text Retrieval Conference, and CLE, like key in French, Cross-Language Evaluation Forum, Europe. This conference has been running by 20 years, and it involves every year hundreds of research groups. And every year, there is a huge amount of data, variable data, the result of the experiment that can be analyzed, mined, and understood. So this is the context. We are dealing here. If you go in the information retrieval field, you go in an experimental field. You need to test the result of your application. It is far away from designing an algorithm. You can evaluate an algorithm by its performance. Here you have to evaluate the result, the quality of your search engine. Second step, you have to understand the user needs. You are a new domain, it's not your domain, you are an expert in visual analytics, let's assume that, and you have to deal with users, what they want, what they need. And you have to understand, you have to learn the same jargon. You must be more or less an expert, a naive expert, if you want, of this new field. And I had to study the Cranfield methodology that I was not aware before. Basically, the idea of the Cranfield methodology is to create a comparable experiment. Because you're running the same story year by year, you want to compare different results. Basically, you want to evaluate your performance. and you want to compare your performance with respect to other people, or you want to know how to improve your search engine. So this is about the needs of the users. That's the final goal, is this one: compare, evaluate, and improve what they did. And now, from our side, the third step, you have to understand the data used in the domain. If you go for cybersecurity, you have to understand what a vulnerability is, what is the score of vulnerability, the severity, blah, blah, and so on. If you go in this domain, you have to understand the data they use. And basically, the data used in an experiment is a triple. You have a set of documents, D, that are documents. Q is a set of topics that are simulating actual user queries. Give me all the documents that are about visual analytics. Give me all the documents that are about computers. And there is a set of relevance judgment. This is the main point, the most relevant point, the most, let's say, expensive point. Is that document associated with the computer? Yes or no? Is that document associated with the visual analytics? Yes or no? And this is a judgment that is done by human beings. Each document is labeled with the relevance judgment. And the yes or no is the simplest situation, but you can go through a set of values, 0, 1, 2, 3, but 0 means not relevant, 1 means relevant, 2 means very relevant, and so on. So human beings, goes to the set of topics, the possible queries, and manually judge the documents, assigning them a relevance score. It is a very costly operation. That's why the result of this experiment are valuable, because you can store them, you want to reuse them. So I think you got the point. If you have any question, please raise the hand or raise your voice and ask me. So this is the data. So try to be back to the underground methodology, understanding the user needs, understanding the data used in that domain. Now you got the point. And let's see the basic experiment goals. You have a set of documents D. You take a query, QI. And among these documents, there are some that are relevant and some that are not. And this is a finite environment. You want to retrieve some documents. And if you run your engine, the software that answers your question, one goal is to catch all of them, the yellow one, that are the relevant document. You want to include them in the result. Retrieve them, please. But in doing that, you can be right or wrong according to two measures. I suppose you are familiar with them: precision and recall. Precision means how is good your result? Does it contain only relevant document, or there are some gray items that are not relevant? So the proportion between the relevant document and the total number of retrieved document is called the precision. In this case, it is 64%. There are some documents that are not relevant in the story. And recall, instead, please get as many as possible relevant document. In this case, it is very good because the answer to our query contains all the relevant document, 9 by 9, so 100% of recall. But there are some noise by gray items that are not relevant. And the result, this is a most important and very important point, is presented to the user in an ordered fashion. You don't see all the result as a set. You see the result as a list. So there are documents that you read as in first position, second position, third position, and so on. And you would like to sort them, having the most interesting in the top, because the user is going to be bored by reading and reading along the list. If the list is very long, it is unlikely that the user is going to read this document in the end. Oh. So ranking is a good idea. Not only you go for position and recall as your goal, but you want to rank the document in the best way, assuming that in this case the relevance is not binary. We have not relevant document, relevant, very relevant, highly relevant, yellow, orange, red, and gray. Not only you want to retrieve the relevant ones, having 3, 2, or 1, but you want to sort them in the right order. And you can see that this is wrong because the yellow ones are not in the top. You want to sort them in this way, having on the top the yellow, after the orange, after the red, and in the last positions, the gray one. Because this is the way in which the end user reads the result. And you have some problem when the order is not correct. This order creates a problem for the user. And we want to provide indications on how documents are being misplaced and indication about the problems, quantity problem. We want to measure the problem rising from the user. Be careful. Information retrieval is a very robust and still active area. The problem has been not solved, not now. And I think that, okay, you can see how to model the problem. Now we are going to have a formal description of it. We have a judgment function that assigns a value between 0 and k, 0 non-relevant, and k highest relevance. In the example from 0 to 3, we model the retrieved result as a vector with an order, first position, second position, third position, and so on, having n elements. Typical values used in information retrieval experiments are k equal to 3, so we have 4 values for the relevance story, and n is 200. We are having a data set of thousands of elements. You focus on the first 200 ones. Why? Oh, sorry. And we have the ground truth function that say, oh, the document's number 5, this is the key of the document, has a relevance 2. Documents 2 as relevance 1. We have a way to resume the judgment, the human being's judgment for each document. And I need something quickly. Okay. I want for a moment to be back to your experience. We are discussing about that. You ask something for Google, and Google provides you a list of results. Assume that you are you get interested in information retrieval, and you ask Google, give me documents relevant for Cranfield experiment, the Cranfield methodology. You put down Cranfield, your query in Google, and you get this result. This is only the first page of several pages. The first one is welcome to Cranfield University. It's not what you're looking at. You want the methodology, not the university. And so you skip it and you go in second position. And again, it's about the university. The third one is about the university. What is they are talking all about cities. So you have to go down to look for new elements. And maybe that sooner or later you'll be bored from that. You will change your query. You will write down Cranfield methodology or something like that. It is very unlucky that you are going to read the elements in the fourth or fifth page. The user is going just to see the first one, the second one. You know what I'm talking about. Let me back to the modeling. So this is our model. This is the numbers we are dealing with. And point 4, now we got the domain, we got the user needs, we got the data. I am doing a class about information retrieval because to make you able to judge a solution of visual analytics in this domain, you must be not expert, but knowledgeable, at least, about the story. So, at this point, you have to understand the analytics used in the domain. Each domain has its own analytics, formulas, computation. And the story, the situation in which the user is going to read the first document, the second one, the third one, and after that he discards the lower one, produces the notion of discounted function, discounting function. What is the meaning before the formula? This document has a relevance tree, so it is highly relevant. This document has the same relevance tree, but this document is less useful for the user because the user is going to read this, and maybe that it stops here. And he will never read this one and this one. So this document and this document, even if they share the same relevance for the query of the user, have less information inside. This is the meaning of discounting function. The discounting function is going to decrease the value of these elements according to the order. The first one, if I, the index I, is less than equal to a threshold X, they are the same. It's exactly the ground truth. So this will have a value of 3, this will have a value of 1. After that, you are going to reduce the value for the user using a log function of the index. And you can, the value of X is going to model impatient users. With the logarithm using 2 as a base, you will be decreasing very quickly the relevance. Meaning that you are modeling users that throw away the answer very quickly. They read the 1, 2, 3, 4, 5 elements and they are done. Instead, if you are, let's say, you're doing a research, maybe you are a patience user, you read the 1, 2, 3, you go deeper in this order. But in any case, the point is that this element has potentially less importance of this. And this is something that has been defined within the domain. It's not our contribution. It is already existing in the domain. You have to understand what they do, the data, the needs, and what they do in the formula, the analytics they use. Now we got to the story. And now, still staying within the domain of information retrieval, you can judge the quality of a result. How can you judge this result? This one, in which the order of the document is wrong, because the yellow document should be on the top and so on. Basically, you can sum how many information, how many pieces of information the user get reading one document after the other. If the user read all the documents till here, for instance, what is the information he got? He loses this document has been lost, and they use within this domain what they call discount cumulative gain function. Is the sum of all the values of all the elements till the position I. So this formula, this is a simple formula, estimates the information gained by user that read all the documents from 0 till the high position. It is a summary measure. It hides details of the story. Till now, we have just used I am just discussing what they use. It was a long story, maybe interesting or boring. It depends if you like the information retrieval field or not, but in any case, it is still an important and vibrant environment. Research is still active in this story, and there's a lot of money in that. Think of Google. If you can improve the search engine of Google, you will be a very rich person. And now we move to the step 5. Now it's our turn. We have to design our own analytics to deal with this problem. I am here reporting something that we did, let's say, 10 years ago with our research group, working with a real researcher in the information retrieval field. First of all, we look to the optimal permutation of the vector that produces the highest discounted cumulative gain for each position I. Basically, visually, this is an intuitive idea. This is the optimal. The best you can do. You retrieve all the documents that are relevant and you sort them in the right order. Rank 3, rank 2, rank 1, and rank 0. If the user reads one document after the other, in each position, the information that he gains is the maximum. And this is an optimistic result. It represents the goal of the information retrieval engine. But we know that the result is not perfect. And we are going to compute using this vector as a reference. We are looking to see what are the relative position of documents with respect to the optimal position. And what is the delta gain, the difference in gain in information between your result, VI, and the optimal result till the I index. Maybe that an example will clarify the story. You run the query, and this is your result. You see that the first, and here I'm just reporting the relevance of the documents. In first position, there is a document with relevance 3, 1, 2, 3, 2, 2, 3, 3. This is not the best one. This is the best one. This is the optimal result. 3, 3, 3, 3, 2, 2, 2, 1, 1, 0, 0. You got the point. Ideally, we want a search engine that does this result. And here we have the gain of the user. The user reads the first element and he gains 3 pieces of information. Let's say this is we are not a unit for that. After the one you get 1, because the relevance is 1, 2, and here you see, from this point on, the discount gain has been introduced. X is equal to 2. So these elements, 3, has not the same value of this. This is value 3, this has value 1.5, because it is in 4th position. And this is even less, this is even less. That gives you the idea of what is the discounted accumulated gain. Each document has a different value for the user according to its position. The higher, the best. And this is the gain that the user gets. I read this, I get this 3. After I read this, 4, 5.26, and so on. And in the end, having read all the documents, I get this total gain, 11.27. Here instead is the same story. Even in the optimal result, a document has less relevance according to its index. This document has relevance 3, this document has relevance 1.50, but it is in the best position. So this discounted accumulated gain has a maximum. In each point, it's always higher or equal to this one. So this is the situation. I think that you got the story. And we want to design a visual analytics environment to explore the situation, to see where here we have some failure, but how to see this failure visually. And just to summarize the analytics, we are comparing the actual result versus the optimal result obtained by reordering. And we have a metric for showing the difference between the actual and the optimal, and the metric for evaluating the quality of the full result, actual and optimal. And this is the representation we designed for that. You see, this is the order of the document, and having the information about the misplaced elements. These elements is above its position, because its relevance, it's 1, is too high in this vector, it should be down. This is correct. It's a 3 in the first position. Correct with respect to what? To the optimal. You see, the first 4 elements should be 3. They're equivalent. So this is in the right position. This is in the right position. This is above its position. This is above its position as well. But we are using a metric, an analytics that give a score of this. This is very far from its position. This one should be here. So it is very far from its real position. This 2 is here, but its position, its best position is here. So it is not so far from the best. So this color, red, is encoding how far you are from your right position. You are above, you are above, you are above. But this here you are really above. The same for below. This 3 is below its position, but is not so below. It's quite close to its right position. This 3 is very down. I think you get the story. So this color here are encoding the difference of position of the elements in the vector, highlighting in green and in red and in blue elements that are in the right position, above or below. And here we are the same for the difference in gain. If you read the first elements here or in the optimal story, it is the same. If you read it till the second position, here you go for having a 4 against a 6. So you're losing 2 in information, and so on. So the 4th column is depicting visually again if you have a loss or gain in reading something. But in any case, the total sum of this will be equal or less than this. This is the best. So this is the idea. It is a simple idea. You don't need a very complex formula in some cases. But here there is a clear highlighting of misplaced elements and the result that this displacement, this wrong placement, has on the gain for the user. And this is the data representation, what we discussed till now. And this is a summary of this representation I discussed. And think that we are representing both the data, that is the order of the documents here, plus derived data. Derived data is about misplacement and delta gain, difference in the gain from the end user, according to the analytics from this domain. And we have to represent it. We didn't discuss the representation till now, but you can easily understand that this does not scale if you're dealing with thousands of elements. So in designing the representation, we are, do you remember the pixel-oriented visualizations? We saw them in the last class. We use something in the sense similar, in the sense that each line here is a pixel line representing a single document. So you can represent hundreds of documents in this way, and the color is respecting this story. Here we have the information about documents that are above or below their position, and here you have the information about the difference in the user gain reading the documents. And you can easily get here some documents that are really below. This is a very, very relevant document, but it's really below its position. Here instead we have documents that are above, they're red, they should be down, and they are producing a very relevant loss of in the gain for the user. Of course, here you have some interaction. Here you are not the numbers. There is no room for numbers. But if you go to touching each single elements, you can have a pop-up window that give you some implicit information. And to describe this function, that is a sum of elements, we have a simple line chart here that represent in purple the actual experiment. This is the result. Here we have the first 200 elements in this line. We are using 2 in the discounted gain, simulating users that are really hurry in reading the documents. Here in red, we have the optimal thing that you can do. If you reorder this document, this is the optimal situation. And here, instead, is the best situation you can get. If you retrieve the relevant document only, and you order them in the best way, this is the maximum that you can produce for the user. And this is our representation, presentation on the screen, in which here you are dealing with the limitation in room. And this is the step number 7, design your presentation. And we skip this, for instance, we recover them with some mouse over story. And we added these lines because they clearly represent the trend of the knowledge the user gets going from the top document to the bottom. And the last point is to validate what you did with the user. Ask user to use the system and show and assess whether or not they are happy with the system if they produce some insight. And one of the most, yeah, I'm not reporting the user study we did, but I want just to report two opposite cases that give you the full understanding of how this system is helpful in pointing out the errors. Look on the left. What is the story? Here, this is our result. It is not in the best order. We can rearrange it, but this is the maximum. So that means that this ranking is more or less good, but the precision and recall are really bad because there are some documents that are outside the story. So in this case, you have to trim you have to tweak your algorithm, not in the term of reordering the result, but in the term of increasing its precision and recall, because here is the problem, the gap between here and here. Here is the other way around. Your result is this. But if you reorder it, you will reach this curve, meaning that your precision and recall are good. You are very close to the maximum that you can get. But your actual order is wrong, really wrong. And you can perceive it with this a lot of red. A lot of documents are in the top on the vector. And there are some very relevant documents that are in the bottom. I think that you got the story. And I stop here talking about this example. Just a last note that we implemented on it a very, I will discuss it later on when we discuss about complex visual analytics and the what-if analysis. One thing that the user can do in this environment is to simulate the result of changing the order. For instance, you see here in the bottom, visually is very evident. It is pretended. This document is below, it's below its position. I will have having it in the top. So the user is allowed to click on it and to drag it on the top. And the system computes automatically the performance of this new engine, reconfiguring all the vector. So that this system in its final form allows also to speculate on how a change in the engine will change the quality of the result. Because modifying an information-driven engine is not a trivial step. It requires programming time, experimentation time, and the system has been intended not only to document the result quality in terms of misplaced documents and the gain for the user, but also giving some possibility to explore what-if analysis, meaning exploring the change that you can, the change effect, not only on a single document, because the basic idea is that if I take this document, I put it here, all the documents similar to it will be in upper positions. And that will have an effect on this curve, effect that can be positive or negative, according to what you are asking to the system. But this is enough for this example. I stop here. And are there around any questions about that? It was a long discussion, but it is very close to your final exam. You will select the domain. You will understand the data using that domain. You will understand the analytics using that domain. You will design your own analytics, and you produce with that a new system. We maybe derived data, a representation, interaction with the system, and eventually also an evaluation with the user, in the sense that you should demonstrate that your system, as I did here. With these slides, I am demonstrating that the system is useful to discover insight. This experiment is wrong because the recall and precision are bad. This experiment is wrong because the ordering is wrong. But this result and this result by themselves are comparable. Is this plus this that give you insight on why this is wrong and where to put your hands to change it. Without this, having only this story, like this, you have no help in doing that. So, producing a visual analytics system is an hard task involving a lot of steps. And the main point is that you must be knowledgeable of the domain you are dealing with. Starting from that, I want to discuss another point. Long time ago, let's say 30 years ago, 35 years ago, more or less, Bess Snyderman, one of the pioneers of information visualization, had formalized this mantra that's still around. The idea is to present the user with the overview of the data, all the data at all. If you remember the car example, this is the idea. You can zoom and filter on this data, selecting subset of it, and ask details on demand. "15 years later, Daniel came, that is, as I said in other classes, one of the most relevant persons in Europe for visual analytics, designed a modified version of this mantra. That is, I'll show you the picture. Take the data and analyze first. In our example, before presenting the data to the user, we analyze the data. These colors, this curve, comes from the analysis of the data. So the idea of Daniel came, it is a very good idea, is before visualizing the data, go for an analysis. And after that, you visualize it, having some analysis already done. And in this visualization, show the important. Here, there is the focus of the relevant point. The colors are pointing out what is important. The curve position are telling the story what is important. After that, you go for zoom, filter, and details on demand. Going for the cycle of visual analytics. You have an image, you have the perception of your image, you go for inside the accumulated knowledge. You do some hypothesis, and you go for exploring the data again. This is the cycle. And here, you run new analytics on it. Visualization and analytics, where the idea of Daniel came is to have the visualization done after initial analysis. This is the rationale behind visual analytics. It is basically a way of thinking. It's not a solution. Each time, if you change the domain, you change everything. But the way of thinking should be this one. And I tried to give you a step-by-step vision of what here I have 8 steps. I have to put it in a list. I did that yesterday evening and this morning. And to have a story, a way of proceeding in developing a visual analytics environment. Disregarding for the moment the perception story, the presentation, representation, and so on. This has been already discussed. I skipped it. And I want to go to another point. Still discussing the role of analytics within representation. We saw step one, deriving new values from the dataset for ad hoc visualization. The information retrieval example we saw now, it is a perfect example. And you now get better the meaning of that is less standard and creative part of the process and heavy. It is not trivial. Here we have this basic stuff, clustering, dimensionality reduction that you're learning about. Tomorrow we will continue about it. And here, something that is very important to me because it remembers me, my research a long time ago, improving the visualization. And what does it mean, improving the visualization? It means that while you are designing your representation, you must take in account issues that comes from data distribution, perceptual aspect, cognitive aspect, everything that can affect your ideal representation. And I'll show you an example. Here we have an image of USA industries. Each industry is a pixel, and it has been plotted on the screen according to its coordinates. And you see that you can have a shape of USA, basically. Plotting the industries on the map, you get a sketch of the map itself. And you have some density differences. You recognize San Francisco, Los Angeles, places, New York, places in which you have a lot of industries. You see you have some areas instead in which the industries are not there. And this density gives you this information, but there is some degradation that results from the collision of points. You cannot read inside here, this is fully black. You cannot appreciate differences in that. And this is done because we already discussed this figure. Here we have an 8x8 pixel enlarged vision of the screen. And the points we are plotting are the industries. Each time that you plot an element here, the pixel is turned on. But if you have 1 point, like here, or we have 4 points, here, like here, or we have, let's say, 10 points, you must produce a difference in that. Not just turning it on and off, as we did here. Black and white is not good. And there is a well-known solution that is called a density map, in which you take these densities, 4, 1, 1, 0, 10, 14, whatever they are, to a color scale. And we have a nice color scale because it is at least designed in order to produce an increasing perception of brightness. This is a contribution in the direction of when I discussed the perceptual aspects. This is a color scale designed taking into account this. Here we are using our perception of colors, and you perceive this scale as increasingly brightness. And basically, you have to map this value to color codes. The higher the density of the pixel, the higher the value from the scale. And this is a very common problem, a very basic InfoVis activity. You have some data that exhibit and the data values. For instance, the number of different data densities. Here we have 1, 4, 5 different values. Altogether, they represent the data values you want to represent. And if we are mapping them to visual attributes that has NL levels. For instance, the number of different color codes. And be careful. Bear in mind that in any case, the number of visual levels of any visual attributes are finite. The color are finite, but also the length of a bar is finite because you have the pixel resolution. We are talking about the representation, not about the representation, but about the presentation, about what the user perceives. And the pixels are finite. So you have ND different values of the data and NL different values of the visual attributes. It can be color codes, but it can be also the length of a line, of the radius of the circle. It doesn't matter. And this mapping is very important. Let's go stick on this bidimensional example. And the case study I'm using comes from the InfoVis conference of 2005. Each year they organize a context that is a game with the user. You have to discover something. But here I am just using the data, not the goal of the context. And we have in this data, we have about 60,000 companies that will be plotted on 800 by 450 scatter plot, having 360,000 pixels. Here you have the image, you remember it. And now we're going to analyze the data, how they're plotted. Basically, we have 126 distinct density values. The collision on the same pixel. Some pixels are empty, white. Some pixels have only one company inside, ranging in 1,633. There is one pixel somewhere here in which we have 1,600 collisions. And the main point is that the distribution of this density is very odd, is very skewed. Among these 360,000 pixels, only 7,000 are active, have been turned on. The rest are white. So most of the image is white. And among these 7,000, 2,500, 36%, has inside only one single company. The rest, in second position, 17%, 1,100 pixels, having only two companies. And there is one single pixel that is the 0.00001% that hosts 1,600 companies, a very high density. And to give you a better understanding of this distribution, here we have the histogram, the frequency distribution. How many pixels you have with just one company? 2,600, 36%. How many pixels with the two companies inside? Here we are, 17%. You see this going down curve. And here there is one single pixel in the end. One single pixel hosting 1,633 elements. And this is very strange, very odd. And if you don't do a careful mapping from year to year, the result is totally useless. And by the way, this strange behavior of this data set is not so strange. Very often, bidimensional scatter plot have this skewed frequency distribution. Maybe you recognize the parcel story. Now you can see the distribution of the parcel. You have that let's say, 50% or something like that, 35% of the pixel have just one parcel inside. And instead, there are some pixels that are full of parcels, but one single pixel here, the distribution like this. Here we have another scatter plot of abstract data. Here there is again other data plotted on the Italy with the same story of the USA. And again, you recognize this skewed distribution, meaning that having a solution for this story means having a general solution. Not only for this data set. It's a solution that you can use very often. So, this is the actual problem. We have a frequency distribution of the pixel of densities, meaning counting how many collisions you have on a pixel. And if you counted the different values, we have 126 different data densities. 0, of course, 1, 2, 3, blah, blah, till 1633 here, the last one. And assume that maybe you can perceive the bars. There is a watchdog story here, remember, that emphasize the difference of the lines. We have 256 color codes, ranging from this dark green to this light yellow. And the question is how to map each of these densities to this. When you design your representation, you design a mapping. When you use to start when you start to use the tree, tomorrow Marco Angelini will give your first class about that. We will share the long class on Wednesday, teaching the tree and the theory about the infovisual and visual analytics. We show you that in the tree you can code. You can code different mapping, linear mapping, logarithmic mapping, or define your own mapping in the tree. Some of them are automatic. Some of them must be implemented handily with your hands, I mean. And how to do that? And why I am so thinking about that? Because the results can be really bad. What is available? What I'm discussing here is something that I did in 2007 with my research group, and trying to solve this problem. And we analyzed what was available around. We have linear mapping and non-linear mapping, basically, already available in the literature. So nothing that you can invent, it's just you ask for them. I'll show you what they are, what they produce. Linear mapping is done using the min-max normalization. Here we have a transfer function. We take the actual value of density. We take density less the minimum. And here we have the maximum less the minimum. We normalize all the data between 0 and 1. Maybe you remember that from dimensionality reduction. And this is a transfer function we have. It is a linear. It is really straightforward, very easy to implement, automatic, but it's totally useful in this situation. This is the physical result you have. All the points are green. Why? Because the odd distribution. These pixels are driving all the story. And here, to give you more precise piece of information, we have the frequency distribution of the code that are being used. Here we have a range between 0 and 256 of the color codes. And you see that most of the pixels here, this is the number of pixels sharing that color. This is the green, the dark green. The dark green has been used by most of the pixels. The image is basically green. So most pixels share very low colors, and we don't like it. Few colors being used. We go from here to here, basically. All these colors are being not used. You see the scale here, green. You reach something a little bit about yellow and orange. And different low density values, because this normalization, are represented by the same color. Density in the range 1 to 10 share the color code 1 and 2. You cannot distinguish them. This information, visual information, is nothing. The value is 0. Nothing to get from it. A second solution that is available in literature that comes from image processing, it is called the histogram equalization, as the idea of mapping the density of a pixel using the sum of all the pixels before it. Each density, dj, is assigned to a color that is proportional to the percentage of pixel before. Before meaning having a density equal or less than dj. And this is the transfer function we get. You see, it's not linear, totally not linear, of course. And it is used to equalize some images. If you have images that are too dark or too bright, applying this histogram equalization, you improve their quality. So you assume this idea, we implemented it, and this is the result that we got. We see that the image has been improved. Now you can distinguish better the denser area, but still there are a lot of problems. Few colors are being used. We have 256 colors. We are using only 39. This is the distribution of the color called the frequency distribution. And the lowest color we use is really high. We start from here. We totally neglect this part of the scale. You can see here we have very few elements in this lower part. There's no green at all here. Why? Because we are using this sum. And this sum is highly influenced by this element. The step 1 influences all the rest. So you quickly move your color to here. You jump from here to here. And even if this is a better encoding, it is not the best. You are using a very high color as the minimum. The range of used colors between this and this, 91 to 255. It is better, but not the best. And different density are still represented with the same color code. For instance, density in the range between 48 and 1600 are in the range 250, 255, are encoded with two similar colors. You cannot read inside here. This is the point. You are saturating the story. To desaturate the rest of the image, you are saturating here. And you are wasting a lot of codes. This is the actual situation. It describes the available solution. Now let's go to our proposal. We had this. We worked a lot on this, and then we explored different cases. But let me explain before, first of all, the rationale behind it. The first point, you have to count that densities and color codes are discrete and finite. And second point, that the colors that are too close to each other are not easy to distinguish. And instead of applying just a formula like min-max normalization or histogram equalization, we need some metrics, quality metrics, to validate the mapping. What we did two different things. One thing is we used a reduced color scale, having only 15 different values, the same color scale, but with the 15 values. If you are familiar by my example with the Color Brewer, the website, you see that they are using the same idea. It makes no sense to present the user with thousands of colors. The user is not able to distinguish them. So it's better to use a reduced scale. This is here there is some wrong pagination. I fix it. This is the color code. This is not 109, 128, and so on. I will adjust it. Just a moment. I fix it right now, so I can see the slides later on. Okay, perfect. So this is the color scale we use. And the other point is, okay, we have to distort the image. It's not possible to guarantee a fidelity. Having this only 15 values, we will have some collision. Different densities will be represented by the same color. As happened, it was happening the same before. Also here we are in the same. Also here we are, sorry. Here and here we were in the same situation. Different densities with the same color. Here the situation is even worse because we have less colors. So we are here pointing to the target of making more clear the differences in the story, hiding the intensity of the differences. And to reduce this degradation, we got the idea to having each color level sharing the same number of pixels. That is the total number of pixels divided by the number of levels. We want to have a flat line of the density distribution. Each color level having the same number of pixels colored in that way. This is the target frequency distribution we want. And this is the result. We implemented an algorithm that was analyzing the distribution data, trying to reach this result. It was not possible because density are discrete and the algorithm cannot ensure this flat line, but you can see, because this you cannot kill it, but you can see that more or less after some values you have more or less a flat distribution on the color. And this is the result of the story. We can claim that we're using the full color scale. We are going from 0 to 255. All the color codes are being used. And we have a maximum color code separation. The user perceives in a very good way the difference in color here. And just to, this is a comparison between the linear mapping, the histogram equalization story, the one-to-one mapping that I didn't discuss. Let's skip it for a moment, and our solution. And maybe you can perceive it here, but I go for enlarging the story on the most interesting area. in the east of America, where we have a lot of industries. In green, we have no information with linear mapping. Using a density function mapping, histogram equalization, you can perceive the denser area, but you have a saturation here. This is the color we are using. The yellow has been amplified as a usage. Here you cannot distinguish what is really important. There is saturation in the high part. Not bad, but not the best. The one-to-one mapping was a bad idea. It didn't work, something that we discarded. And this is our result. And here you can see that all the colors of the scale have been used. We have orange and yellow. And you can distinguish better in this area this strong point, and the points that are just below, the red and the orange. You have most of the resolution is available here, even if you have only 15 colors. So we claim that this is a good result, better than this. And the last point was to assess a claim with the formula. We cannot say just this is better than this. Visually, I can convince you, but to be more formal, look at that. Also here we have a lot of dark because the green is not available. Here instead we rescue the green, so we can picture out some low dense areas in which there are some industries, little number, in the initial range of the scale, 1, 2, 3, 4, 5, but they have been not killed by the equalization. But if I want to be more formal, the formula are very simple, but let's go to what is the goal of this formula. How many color code is the mapping using? And we call the color scale usage. The higher, the better. We want to use as many colors as possible. And what is the color scale active range? The interval of this. What part of the range, what part of the color range scale we are using? And what is the color separation? How can I easily distinguish two close colors used in the mapping? We define these three metrics, these three formula that I don't discuss because they're a little bit boring, but they're very simple. And let's back to something that maybe you remember, the partial data set. You now can distinguish its frequency distribution of densities. Now you know that here there is some part that is harder to distinguish because of a lot of collision. Here there are some points in which you have 1,000 parcel on it. And here there is the comparison also with the grayscale of the linear mapping, the histogram mapping. This one-to-one here, it reveals some interesting issue. And what is, in my opinion, the best one, the uniform color scale transfer function. You can perceive better the trend here. You can perceive this cluster here, and you are preserving the lower R. Here, this some gray here that you cannot distinguish. You get it. Because the highest part is well represented, but you cannot look inside here. And this is good, still good. The one-to-one is still good because you perceive something inside. It's better than linear. And here better is substantiated by the matrix. What about color scale usage? Here is 1, here is 1. In the other cases, it's 0.5, 0.18. What is the, let me back to the metric. What is the active range? Here the active range is 1. We go from minimum to maximum. Here using only the right part of the scale. Here in the linear, it is one because we go from minimum to maximum, but most of them are in the white. And here we have similar results. And what about the color separation? It is the highest one because we have only 15 colors. Basically, these metrics are beating the other ones. So our claim is substantiated by formulas. And this concluded this part of the story, where the goal of this, I will put these new slides on the web today. We're discussing an example of complex representations, something more than single colors or single histogram or bargrams or something that we saw radial representation. Basically, the combination of them, pixel-oriented visualization, or combination, like here, histogram, bargram, plus one level tree map. A full example of visual analytics, a little bit long maybe, but they give you the feeling of the difficulties that are behind. This is the final result. But this has been obtained by an accurate analysis that as a prerequisite to have a good understanding of the domain. And in the end, we saw some nice usage of derived data. Here, it is quite impressive, very simple to get it, but still using visualization of derived data. And here we have some analysis of the basic mapping. This is just about the visualization. And there are some perceptual issues in that. Here, I'm not going, I will be back on this. Having this reduced scale comes from the idea, some precise ideas about perception. So here there is more attention towards how we behave in looking at colors or grayscale. And that can be used as inspiration for you, for the exam or for your work in this area, if you will work in visual analytics. And remember the complex activity that are behind either the simple idea of improving this density map. I remember the work we did on it, a lot of work. For a result that you see, oh, okay, nice. You convinced me, it works. But we really worked hard on this to get this result. Okay, and okay, we are very close to the end of the class. Are there any questions around this? I will put on the web the new slide. I will put on the web the original paper about this story. Maybe there's someone who is interested in it. It is a very low-level activity, but it's fundamental. This is what you do otherwise. No, not useful at all, partially useful. Much, much, much better. Just in a simple point as plotting a scatter plot. So that should make clear that even a simple visualization like this may be a complex activity. And I want to move to another point. I stop my sharing. Okay. You should see my browser. And now I am moving towards a very recent work of my research group. If you go on the home page of the work group, I pointed the link. in other slides. You can get a lot of prototypes and ideas, and I want to show this simple idea, not so simple in the end. Do you remember the guidance story? You remember the fact that when you go for a selection, you can have this paradox that you ask for something and the result is empty, and you don't know how to relax your query. Or the other way around, you have too many elements in the result, and you need guidance. And we decide this system. This is a demonstration of the system. The visual part is very limited because the focus is on the filter. Basically, we are dealing with the wine data set. Maybe now you are more familiar with it. You can recognize for the attributes alcohol, malic acid, the ash, alkalinity, and blah, blah, blah. And here we have a bidimensional projection of the data set. It might be a PCA projection. It can be, here you can select different projection, different data set. But let's stick with the wine story. The shape of this is not relevant. What is relevant is the fact that you are trying to filter the elements. You have 178 wines in your data set. And it is a representation in which each wine is a single point. A bidimensional projection on two attributes, or a PCA on it, on MDS, or whatever. And here we have some filter on it. This is not the final version of this prototype, but just to give you the idea. We have the filter is done having some widgets. A widget is a visual element that allow you to select the data, dealing visually with some elements. For instance, we have the alcohol scale. Just focus on it. The alcohol is ranging between 11 to 15, more or less. And we split the scale in 3, 4, 5, 6 slots. You can select here, and you get all you cannot read it very well, but I can alert. No, I mean, you are using your computer, so the resolution is very high. One of the single advantages of this teaching by remote. You can read it that we are dealing with the wine having the alcohol value between 11.7 and 12.3. They are 31, about 178. And this is a way of selecting the data. You can select more than one single element. You are selecting more and more wines. You can even go for disjunct selection, selecting alcohol in the range 11.7 and 14.2 to 14.8, high gradation, high alcohol, low alcohol. And this is the way in which you can use this scale. It is a prefixed scale. You can also have a slider. We have them in other implementation. And we have an additional way of filtering using the box plot. And this is really nice. You remember the box plot story. And here you have a box plot. Here we have the median. Here we have the minimum, the maximum, but the outliers. And here we have the quartile. For instance, you can select the outliers. Give me all the wines, 5 of them, that are outliers, in the sense that the alcohol is very high, too high, and they are above the normality. They are the outliers. And the other way around. Give me the low alcohol wine as outliers. And you can see them on the screen. We have 4 of them. So we're using the box plot to basically to as a filter. Give me the normal wine, where normal means the wine that are the 50% of the wine, this is more or less 50%, you see, 49, that are in the middle, around the median. They are in the average. And you can combine if you want. You can ask this one, the outlier for the alcohol with the lower quartile interval, and so on. And this is the point of using the filter as using the box plot as filter. And you can enrich this. You can have some two course. This is a discrete, a finite set of steps. Yeah, only 6. If you can have a slider dragging them. You have the box plot. You can have a frequency distribution. Why not? And you can use the frequency distribution as input. So the one idea is to combine different means for, let's say, filtering the data. And these are on single attributes. After that, you are combining it with multiple queries. So give me, let's say, all the wine with the high alcohol, 51, that, and I want to combine it with other attributes in AND, with this low value of hash. The result is empty, because no wine has this high level of alcohol and this low level of hash. But this information was already available. This pattern behind the interval show you the fact that the element in the selection have some values in these intervals, but not here and not here. So selecting here or selecting here will produce an empty result. Also here. This is a new idea of guidance. Avoid or point some elements that will provide empty result. And here we have other indication how to decrease the result. There are too many, 51. I want to decrease them. Here you see this arrow down red. It means if you click here, you will reduce the number of items. And here we have an indication that will kill 50 elements. Only one in the result. This will kill 41. This will kill 23. And the system update again. And you still have the control. You can see, for instance, I didn't discuss that. All these elements, yellow elements, fully satisfy this interval. All of them are within this interval, or this one. They are partially in this partially, and we are not here. And we have guidance for reducing with the feedback about how many elements we are going to reduce. And when we are eventually, we got a very, very, very little result, only one wine. I miss here the interaction. No, we have the interaction. I forgot it. This is all the values of that wine. Only one element here. And if I want more, how can I relax my query? Look at this. This blue arrow points some way of relaxing the condition. If I relax this, I will get +2 wine, +1 wine, +7, +4, +1. So I can go here and I include 7 elements in the result. I think you got the point. Maybe I will get the final environment that is a little bit more sophisticated than that. The one on the point is that here we have one symbol increasing the result size, and we need a mouse over to get the number. In the new prototype, we have a varied number of arrows, 1, 2, 3, giving a visual indication. And after that, the mouse over gives you a more precise idea. But this is a nice way of filtering the data. We have presented this paper last year at the DIAG conference. And we got also a prize for that. Because this is a simple idea, but basically we are extending the notion of guidance, but this is only partially solved. We are trying to make the user aware of the reason of the result. If I click here, and they come up with 79 wines, and you see, the hash here is full of this will not change the story. I mean, this is a strong reduction, but still staying in the interval. You see this arrow down, and we have less 78. That produces an empty result. But these dashed lines that are replicated, let me make it a little bit more complex. 25 wines. We are in this interval of alcohol, in this range of the box plot, here, 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 and the dashed areas try to give you the perception of how these different attributes are affecting the result. But it is not a simple task. I am not totally satisfied with this. That can be improved. And again, this is not part of the representation. This is part of the interaction, of the simple filter activity. What in reality still it is part of the representation. If you think to the car data set, basically the user had at disposal only this way of doing. There were some bar graphs around, and the user were able to click on them. And there are some guidance for increasing the result when it was empty. If you are in an empty situation, there were a guidance, but the guidance was about the car inside an interval. Here, instead, for each interval, we have this information. Okay, I think we are done. Is there any question about that? And that basically concludes the story of complex representation, including the filtering activity. Don't forget this story. You should be inspired by these ideas in your final exam.